Hi, I'm Derek, and today we're going to build a robot. Now, there are a ton of videos out there that show you how to make smaller robots that run on 9-volt batteries and break when you step on them. I'm not really interested in those. I want to build a robot that's more robust, something that I can use around the house. So with that in mind, I've got this old electric wheelchair here. Now, electric wheelchairs are kind of pricey brand new, in the $2,000 range, but due to their target market and circumstances, you can find one used for pretty cheap on places like eBay, Craigslist, estate sales, etc. I picked this one up for about 300 bucks. Now, 300 bucks is still a lot of money, but that 300 bucks pays for 2 high-powered motors, 2 12-volt batteries to power the motors, and a nice sturdy steel frame to support all of that, plus a human weight. I think it's worth it. So with that, let's see what we can do. Now, an electric wheelchair controls its motors through something called a microcontroller. A microcontroller is just a fancy word for a microchip that controls electric circuits. That's what maps joystick position into wheelchair movement. Now, even though this electric wheelchair came with one, we're just going to rip it out and use an Arduino instead. The simple fact is that Arduinos are open source, which means there's a lot more documentation, which means they're a lot easier to program. Now, if you're interested in building robots and you've never heard of Arduino before, don't worry, I left a link in the description. I highly recommend you just pause this video real quick, go follow that link, check it out, and come back. Go ahead, I can wait. Cool, now that we're on the same page, we're going to be using an Arduino Mega for this project. You could get away with using an Arduino Uno or something similar, but Arduino Mega has extra pins, and as we add more and more features later on, like arms, lasers, etc., we're going to need them. Now, if you've done your research, you'll know that an Arduino only puts out a max of 5 volts. These motors, however, run in something in the realm of 12 to 24 volts. That's where this guy comes in. This is a Megamoto. It's an open source motor shield that plugs into the Arduino. Instead of connecting the Arduino to the motors, we connect the Megamoto. It connects to the main power supply and sends electricity to these 2 terminals based on what the Arduino tells it. So we connect the shield to the Arduino like so. And boom. So the power circuit gets connected to the motor terminals based on the logic in these 2 things called MOSFETs. M-O-S-F-E-T if you're interested. And then these little jumpers down here determine which pins the Arduino can use to talk to it. This is handy because each Megamoto can only power 1 motor. But we can stack another one right on top of it to control our second motor as long as it's configured differently. I soldered some wires into the top one so that it can hook up to the first one's power terminals and run off the same battery circuit. And this is going to be the circuitry that controls the motors. Just remember to configure the pins on the top shield so that they're different from the ones underneath it. So this is a circuit diagram of our new setup. If you want to get a better look at it, just rewind the video and pause it. Now that the parts are all hooked up, we just got to program the Arduino to get it talking to the Megamoto. The first thing we do is tell the Arduino what pins we're using. And since there are 6 of them, we can just use some internet magic to save some time. Cool. Now we write the setup method to tell the Arduino what to do every time it turns on. And I'm going over this part kind of quickly because it's pretty standard stuff for an Arduino. If you haven't worked with Arduino yet, you can tell by looking and some quick Googling what all this stuff means. So now we can get to the programming. The Megamoto's manual explains that the A and B pins can have a value between 0 and 255 written to them. The bigger the difference between the A and B pins, the more current gets passed through. So if one pin was set to 0 and the other to 255, then the motor would have the entire current passing through it. If the difference between them is 0, meaning they're set to the same value, then something interesting happens that we'll get to in a minute. Starting out, we'll just use a small difference, just in case. Now the motor's direction is defined by the pin with the higher value. So if the value for the pin connected to the red wire is higher, then the motor moves forward. If you want to go reverse, well, figure it out. Oh, and don't forget to set the enable pin to high or else the motor won't get any power. Then we write a similar code for reverse. And we probably want this thing to stop at some point, so we should program that as well. When we set the value of the pins equal to each other, the Megamoto shorts the motor circuit, meaning that the red and the black wires are directly connected. This creates a closed loop in which the electromagnetic force that propelled the motor suddenly halts and becomes a source of drag for it. This drag eventually brings the motor to a stop in a phenomenon called eddy current braking. EDDY current. I left a link in the description. If you want your robot to just coast, you can set the enable pin to low, which disconnects the circuit and lets the motor freewheel. And what the hell, let's test it out to see if I made any mistakes, and it looks like I did. Oh, I haven't written the main loop yet, right. So the loop is where we put the main set of tasks we want it to do. Other than that, it's exactly what it sounds like. Right after the robot turns on, I want it to brake, so I take that method that we just built and I plug in the variables for the 2 motors. and then I tell the Arduino to give us a little message about what it's doing. This is just an extra step for debugging. And now we do something similar when we want it to move forward. And there we are. Now, before we turn this thing on and test out our code, there's one more thing that we have to take care of. Each wheelchair motor has its own brake that sits in a cap right here. If you apply current to the motors without first applying current to the brakes, you're going to get a lot of screeching, a lot of sparks, and you're going to have a bad day. So we'll just pull them out. Now the cap comes off by undoing 2 Phillips head screws, and then the brake is attached to the motor by 3 hex head screws. I wish I had something that I could show you guys, but in the time between getting this wheelchair and making the video, I sort of pulled the brakes off and lost them, because I'm unorganized. But anyway, let's turn it on and see how it works. Yeah! So now that we know our motor controllers work, we can move on to the next part, which is programming sensors. Let's get to it. So the first kind of sensor we'll use is the ultrasonic sensor, because they're pretty cheap and you can find them at any hobby store that sells Arduino stuff. Since they're so ubiquitous, the Arduino code for them is a quick Google search away. It's pretty simple, so I won't go into detail about how it works, but I did set up an example so you can see it in action. So I just upload the sketch to the Arduino and open the serial monitor. These things aren't super accurate, but you get what you pay for. As you can see, there are minimum and maximum distances where the readings get kind of screwy, so we have to design around that. So as you can see, I very securely fastened the sensor to the robot's chassis. Yeah, that's not going anywhere. And now we tie all these parts together in a new sketch that will let our robot explore the world without bumping into stuff. And since we did most of the heavy lifting in the first 2 sketches, we can just copy a lot of that code over. So first we copy the pins in the setup methods, making sure that the new values for the pins are updated. Next we need to take the main loop from the sensor sketch and turn it into a method like we did for the motors. We'll get rid of that delay since we don't need it anymore, and in its place we'll add an extra line of code so that it returns the distance measurement to whatever calls it. This will allow the loop to make decisions based on that value, rather than just printing the value out to the screen and forgetting about it. Next we copy over the motor control methods and move on to the main loop. Now, before the robot does anything, it should do a scan to make sure there's nothing in front of it. Earlier I said that the sensor has minimum and maximum distances that it can measure, and through some trial and error I found the distance can be anywhere between about 2 centimeters and 540 centimeters. So as long as the distance it senses is between those 2 numbers, we're all good. And since I mounted the sensor about 20 centimeters behind the front edge of the robot, I have to include that in the minimum distance. Moving on, if nothing is in the robot's immediate vicinity, we want it to move forward. But this loop is going to be executing several times a second, and I don't want to keep writing the same value to the motors over and over again. It seems sloppy and unnecessary, so we're just going to add a variable that the Arduino can check before it does anything to the motors. This seems like an extra step, but it'll come in handy later on. So then we come back to the main loop and use another if statement inside our first one to check the new variable. This new variable just says, if you're not going to change the value, just leave it alone. And now we get to the obstacle part. When the robot sees an obstacle and decides collision is imminent, it should stop and turn. But how far? How do we decide what a proper turn is? Well, we already have a method to decide whether or not to go forward, so why not reuse that for this new situation? The simplest solution I can think of is to call the turn method, delay for a bit, and then go back to the beginning of the loop. If the robot is still facing an obstacle that's too close, it'll just keep turning until the path is clear, and then move forward again. Looks good to me. Let's try it out. So now we have proof of concept, but our design is still pretty basic. Our robot's most glaring shortcoming is its large number of blind spots. Now all we need to do to fix the problem is just add more sensors. I'd say 7 just to be on the safe side. So ideally we'd have 2 looking forward, 2 on the front looking out to the sides, and then 4 more on the back doing the exact same thing. I showed you the basic way to code sensors, and you can copy and paste that code 7 more times, but that's kind of messy and cumbersome. So in the next video, I'll show you how to code things in a way that makes adding new hardware easier, and I'll show you how to make the robot do something more interesting than just stopping and turning. See you then!